Whisper is open source speech transcription software developed by OpenAI. It allows you to convert audio into text. Now, just recently, OpenAI released Whisper Turbo, which provides an 8x speed up over the largest Whisper model. I'm going to do a few things in this video. I'll provide a free Colab notebook allowing you to transcribe audio, including YouTube audio, using Whisper Turbo. Then I'll briefly describe how Whisper works and show how to fine-tune it on specific words or accents, including how to prepare a dataset for doing that. And last of all, I'll show you how to set up a server so that you have a fast Whisper endpoint. Let's get warmed up with a quick demo. I'll put the link to this Colab notebook in the description. This allows you to convert audio files, MP3, WAV, MP4, into text, and you can convert into literal text or JSON format or VTT, which is a subtitle format, or SRT, another subtitle format. You can also download the audio for a YouTube video. This is how I generate subtitles for the YouTube videos on Trell's research channel. So you want to first connect to the instance, and if you're going to convert some audio files, you need to let the instance boot up before you can do that. And I'm going to add then one of my MP3 files. So I've just uploaded a short MP3 file called MP3. And now I could just run all the cells and it will automatically transcribe this. But we can step through briefly and show you how first we're installing Whisper, the OpenAI package. And then we're going to iterate through all of the audio files, MP3, WAV, or M formats, increase their size, and transcribe each of those one by one. And that should then provide us with the transcribed files out here. It'll actually give us all of the formats here on the left-hand pane. Now, you can also use a custom Whisper model that you fine-tuned by providing the Hugging Face repo ID. I'm going to describe how to fine-tune that a little bit later. And last of all, if you want to transcribe YouTube audio, you can provide a YouTube link just like this, and the script will automatically download the M4A audio, and then it will start to transcribe it. So the transcription has been complete on this input file, and I'll quickly show you first the text. So you can see here, it's a short amount of text. And I'll show you the VTT file, which is the transcript format I use for YouTube. And then for Twitter, if I upload a video, I'll use SRT. Both of these have got timestamps and text within them. So how does all of this work? Let me give a very brief description, and I'm going to draw from an OpenAI blog that shows the architecture of Whisper. So Whisper is actually a transformer model, or at least it includes a transformer within it. It takes in audio and then it spits out text, which is actually a series of text tokens or subwords. Now, if I break that down a bit more, audio is a wave, that noisy wave you see if you see a sound wave recorded. Well, that has certain frequencies. And so what's done is that wave is converted into its representative frequencies. And furthermore, it's converted into the frequencies as we would hear them as a human, which is called a Mel spectrogram. And that information is taken in chunks. So it's split into small chunks. Often there's a larger piece of audio, 30 seconds, and then that's split into sub-chunks that are fed then into a convolutional neural network. And this is the encoder. And what that does is it converts the representation of the audio into vectors that represent the meaning. And those vectors representing meaning then go into a transformer, which is a decoder. But this is a classic transformer. It has attention layers within it and feed-forward layers. And we'll see that in a little more detail when we do the fine-tuning. But essentially, it takes in some start tokens indicating the language like EN, and the task, which is transcription. Sorry, that's quite small there. And the goal is then to predict a series of follow-on tokens. And those follow-on tokens are computed with the benefit of this incoming audio information, which is in vector format. So by the time we get through all these layers, it's 32 layers in a standard transformer, not standard transformer, but rather the Whisper transformer design. We get to an output where we have a prediction of the sequence corresponding to the 30 seconds of audio right here. Now, what is Whisper Turbo? In Whisper Turbo, they essentially pull out a lot of the middle layers. This is called pruning, and they only rely on 4 of the layers. And then they do subsequent fine-tuning. They actually train on 2 epochs of a very large amount of data. And why does this work, or why does it make sense? Well, it's beneficial because if you only have to calculate through 4 layers instead of 32, you get an 8 times speed up. That's where the 8 comes from. And why does that not affect performance? Well, it turns out that a lot of transformers, probably after training, they have too many layers, and you can just take some of them out without affecting performance too much, provided you do some further fine tuning on it. And this is often an approach that's taken with distillation, if you want to check out my video on distillation. But in this case, they don't actually use, I'm going to say something technical now, they don't use KL divergence for improving the weights after pruning out the middle layers. They just do straight cross entropy loss on 2 full epochs of data. So they actually use quite a lot of data after pruning out the middle layers to get a faster turbo model. And so that was a whirlwind tour of how Whisper works and how Whisper Turbo is essentially Whisper, but with 28 of the 32 layers removed and then fine-tuned to stabilize performance. And the performance is actually very close to the large model with 32 layers, but it's 8 times faster. Now, let me introduce Faster Whisper for the sake of adding more terms and models. Faster Whisper is an inference library. So inference library, you can think of transformers. That's a library by Hugging Face, and it allows you to produce tokens using language models or Whisper, for example. Well, Faster Whisper is a different library. It's not transformers. It's built on a different basis, which is called C-Translate 2. And C-Translate 2 is a library that allows you to do faster inference, and the specific implementation leveraging that is called Faster Whisper. So by using Faster Whisper, you're able to not only get the benefits of Whisper Turbo, but you can also get speed ups because inherently the C-Translate library is faster than Hugging Face. What does this mean in practice? It means when we fine tune a model, or if we just want to inference a base model, we need to have the model in a C-Translate 2 format that is going to allow us to run the Faster Whisper library. So very quickly, here we have Faster Whisper. This is the library that allows you for faster inference than transformers. And in order to use this library, you need to have converted your model into a C-Translate 2 format. So we'll use some conversion scripts here. Now, just for the jokes, not even joke, because this is a serious project, there's also insanely fast Whisper. If you want to, I don't actually know to what degree this is faster than Faster Whisper, but it's an option to look at. And there's also incredibly insanely fast Whisper. No, I'm only joking. It doesn't go that far. We're going to keep things somewhat simple and focus on Faster Whisper. And that is the type of server we're going to set up. So just to add one more layer of abstraction, if you have a library like Faster Whisper, you are then able to build a server based on Faster Whisper. So there is also Faster Whisper Server. And that is the library we're going to use to set up a server that deploys Faster Whisper using Whisper Turbo. With that, let's move on to Whisper fine-tuning. Why would you want to fine-tune Whisper? A few reasons. One is you want to add new vocabulary. For example, there are new words that have come out after the training data of Whisper has been fixed. Maybe you want to improve performance on a difficult Irish accent. Maybe you want to improve performance on uncommon languages. I'll note that if you want to try this, you need quite a lot of data. And you'll also need to be careful that the tokenizer is going to reasonably support the language. If you're using a language that is a very different tokenizer than Whisper, that's probably going to be difficult without also redefining the tokenizer. So let's move to preparing some data for fine-tuning. We're going to need some sound, which means an MP3 file. We're going to need some text that is a clean transcription of that sound, because that's how you train, using the clean audio and the clean data. And given the clean data, you get the model to make a prediction. You compare its predictions to the clean data, you see what the error is, and then you back propagate that error to make the model more accurate. As I always suggest, I recommend splitting the data into training data, which will be used for error correction in the model, back propagation, and then validation data, which will not be directly used for training, but rather to measure the performance improvement as we train the model. One small note we'll get to later, we're not going to update all of the weights in Whisper. We're only going to update a subset. In fact, for every large matrix or every main large matrix in the linear layers, we're going to apply adapters. Adapters are smaller matrices that, when multiplied, give a matrix the same size as the larger matrix. Like here, we have a matrix of 8 by 1024 and then 8 by 1024. And if we multiply those, we can get a matrix that's 1024. And what this allows us to do is actually not update the main weights of the language model, but rather update these adapters instead, which is a lot more efficient, less compute, and actually avoids us overfitting too much as well. This is called low rank fine tuning, and you'll see us do this a little bit later. So for all of this fine tuning, we're going to make use of the Trellis Research Advanced Transcription repository. You can find this at trellis.com/advanced transcription, and it has all the scripts. It's a paid repo. You can buy one-off lifetime access, which includes future scripts I upload. And it now has scripts for training speech-to-text models, text-to-speech models, and speech-to-speech models. With Whisper, we're talking about a speech-to-text model. So we'll be focused on the scripts that are here. And the key notebook, I've now consolidated everything into one notebook for data preparation, fine-tuning, model conversion into C Translate 2 or into OpenAI format. It's all in one script called Fine-Tuning Whisper. So I've started up a RunPod instance on a GPU. You can actually probably do this on your Mac if you have a Mac M1, M2, or M3 by setting the device to MPS. Probably it's still a bit slow to do on CPU. I'm going to run on RunPod, and I'm going to use the fine-tuning template that's in Trellis Research one-click LLMs. If you just search here for fine-tuning, you'll find a link that will allow you to set up an instance with the right settings. So typically I'll just use an A40, and then here's the Trellis notebook for fine-tuning. Just to note that this repo also now has a link for a one-click template here for Whisper. If you just scroll down to Faster Whisper, we'll check this out a little bit later in the video. But let's get started with fine-tuning. So I've got my pod up and running. I connected via Jupyter Notebook, so connected here, Jupyter Lab, and I'm up and running here with my notebook called Whisper Fine-Tuning. So let's go step by step through this. We've got the installation, dataset generation. Then we'll actually push the dataset to Hugging Face Hub, load it. Then we'll prepare the dataset so that it's in the right format for training. And then we're going to run the training. Then we'll evaluate performance. Then we'll push the model to Hub in Hugging Face format. And then additionally, we'll push it in OpenAI format. So it works with the Colab notebook I showed you earlier, this one here. And then we'll push it in C Translate 2 format, which is necessary for faster Whisper. All right. So for the installation, we're going to run a few cells here. FFmpeg is an important audio processing library that we'll need to update. So we'll install that, and we'll install a number of other libraries here, including transformers and parameter efficient fine tuning, which allows us to do the LoRA fine tuning. Now you can use quantization. Most likely I haven't tested it out, but this would allow you to reduce VRAM. Either way, Whisper models are very small. They're only gigabytes in size, so they'll easily run on Colab without even using quantization. Next, because I've installed HF Transfer, I have to set this environment variable to allow for fast weight downloads and uploads, although the weights are small, so it's not that big a thing. And then log into Hugging Face Hub using a token from your Hugging Face account. Next, we're going to pick the model to fine-tune. So we're going to fine-tune Whisper Large V3 Turbo. And it's called this way because it's the large model, but with those 28 layers removed, so then it's made turbo. And we're also going to set the language that we want to transcribe through and the task, which is transcription. Now you can allow Whisper to auto-detect the language. It takes a bit longer because that means that token isn't pre-filled, and it can lead to little higher error rates. So if you know for sure the language, then it's good to specify it. Here I'm just specifying some folder names, my org. Then I'm going to define a name for the trained adapters and the trained model. Next, we have to generate data. So first thing to do is to upload some training and some validation audio. That's actually all you need to get started, because we're going to automate the process of generating a clean transcript for those. So I've uploaded train MP3 and I've uploaded validation MP3. And quite simply, I've recorded myself for a few minutes talking about some large language model keywords. Actually, I've got the keywords listed here. So these are some keywords from about a year ago when these types of language model were all hip. And I literally just read these out, just talking in between and talking about the different models so they would pick up on the words. And the reason I picked these words is because the language models are not familiar with these words. Whisper is not familiar, so it won't quite get these right when you try to transcribe these words. And then I shuffle these words to make validation keywords.txt, which is right here. And then I read these out, and that gives me a validation piece of audio that I can run and see how performance is doing if I've trained on the training audio. So you need to upload train.mp3 and validation.mp3. They're the two key files to upload. And our goal now is to create a transcript from those, which will be imperfect, then correct the transcript to get a clean transcript, and then use those files for training. So we're actually going to use Whisper to transcribe that. And I'm setting up a function here that's going to process each of these audio files. So it's going to process and then create VTT files and save them. And I'm going to run that for train and for validation. Now let me just correctly make the imports. I have to set my file names and then run for training and validation. And what this will give me is train.vtt and validation.vtt, which I've also run earlier. And that is now complete. So we can take a quick look at the VTT file. And you can see here that already there are things that are incorrect, like phi, it doesn't know about phi2, so it spells it with a Y. And decLM, it doesn't know it's DECI. So these are the mistakes that the raw model is making. And we now need to clean this up. And you can clean it up manually, just literally type into this file and save it. But I've also written a short script to help you automate. And the way this script works is by using OpenAI in order to clean up the script for us. And it does it on a line-by-line basis. Specifically, it will provide 5 lines of text, 2 lines before, 2 lines afterwards for context. And then it will denote the middle line as the target that needs to be cleaned up. And it will ask OpenAI based on the list of keywords. So I provide in the keywords here. It will ask OpenAI to clean up that one line, and then it will iterate through all of those lines. So you can see the prompt here. I want your help in correcting the following VTT file. I'll provide up to 2 lines of text before and after the line that needs correction. Do not modify the timestamps or any other lines. So here's the combined up to 5 lines, then the target line to fix. The keywords, so it knows what the keywords are that should be fixed, and then it returns the target line. So I need to install OpenAI, and then I need to enter my OpenAI key, run the script, and you can see it's just iterating through these line by line in order to create a corrected VTT file. So we'll have a corrected train corrected, and we'll have validation corrected. And this will work if you have longer data as well. It'll just take a bit longer to process. So let's take a quick look at the corrected file. You can see here it's got phi2. I'll note that even I'm using a strong model here, GPT-4o. I tried mini and it just kind of makes mistakes. And even with GPT-4o, I don't know if I'll spot a mistake here. But yeah, like this here should be Claude, but it's saying Claude, C-L-O-D. So this clearly should be Claude, so I'll manually fix it. And let's see if there's anything else. Yeah, see this here is wrong as well. It should be Claude 1, Claude 2. I think it's 2.0, I'm not even fully sure. But either way, you want to have this fairly accurate so that you get good results. And that will have done the same for the validation file, which we care a bit less about fixing because it's just for validation. So next, we're going to chunk the audio. So we have these MP3s that are a few minutes long, could be even longer, like an hour. And this needs to be split into 30-second chunks. That's the dataset format that the trainer is going to expect because Whisper has a window of about 30 seconds. So I'll install WebVTT and I'll process the validation corrected and the train corrected files in order to give me chunks, which will then be uploaded to Hugging Face Hub. Now, there's nothing particular happen here other than breaking that into 30-second chunks, which you can see now appear on Hugging Face Hub. So we have 6 rows of training, 5 validation, and we have some audio. I don't know if you'll be able to hear the audio actually from here, but I have a short snippet that corresponds to this text, and I've got the start time and the end time. That's also important for the training, so we pass in timestamps. So now that we have a full data set, we're able to load that data set right here. Now, just to note that if you do have multiple MP3 files and VTT files, that's fine. You can still just upload them at the start. They will all be converted. And if you want them all to be chunked, you can use this script here for processing multiple MP3 or V2T files. So I'm going to download now my dataset from Hugging Face Hub and start to get ready for training. So for this, we're going to need the Whisper feature extractor, the tokenizer and processor. The feature extractor is for the audio, the tokenizer is for text. And we'll prepare the dataset. So when the dataset is prepared using the processor, which basically will help to set up the tensors that we need for training. You can see here the format of data. We have a path to the audio file. We've got an array, which is an array of the audio data, the sampling rate. And just to note that I think when you feed in data, we're going to need to feed it in effectively at 16,000. So that's why actually when we do read in the data, it's going to be sampled at 16,000 on the fly. So I'll run this cell. And we're now ready with the data set. It's not formatted right here. You've still got audio, text, start and end time, but it's going to be mapped now in this stage using the prepare data set function. And that should run pretty quickly because it's a short data set. I do have an error here. And the data set now has been mapped. So now it's no longer audio, text, start time. It's literally just a list of input features, which will be tensors, and then labels, which is what we're trying to target with our generation. Same for validation. And then, of course, we can print the entire data set. And we're ready now to move on to training. So there's one more data set preparation, which is around padding and also setting to ignore the padding tokens. And that's going to be done within the data collator. So we have the data collator that's being initialized by passing in the processor. We're also going to define some custom evaluation metrics. And I should mention a lot of this part of the script in particular comes from a base original notebook by Hugging Face on training the original Whisper. So here we're going to set up what's called the word error rate. It will just measure the percentage of words in the transcription that are incorrect. And we're going to use that for computing metrics. So we're ready for computing metrics and we're going to load now the model. So we're just loading here the Whisper Turbo model, nothing too fancy there. And now we're going to apply LoRA. So as I mentioned earlier, we're not going to train all of the weights. We're just going to train these adapters. And specifically, we're going to apply the adapters to the linear layers here. So QVKO and FC1, fully connected layer 1 and 2. And you can see here's the architecture of Whisper, the turbo model. It's got the encoder, which is a convolutional network. And then it's got, it's got some transformer attributes here. It's got attention and fully connected layers here. It's just got these convolutional layers here at the start. And then in the decoder, you can see there are those 4 layers instead of 32. And then we've got attention and we've got feed forward layers here. So typically we will fine tune the linear layers. And we'll do that via adapters, which I've just shown here. If you did want to change to a different language that has a very different token distribution, then you might want to train the embed tokens, the embedding tokens, which will not be trained with LoRA. They will directly be trained in their full wave format. And that's something that can improve accuracy if you are changing language or token distribution. So you'll see, as we're doing it, we're only training about 3% of the total parameters. And we're ready now to move to the trainer. So we'll define the output name, the batch size. I'm using a small batch size because we've very little data. I'm not going to use gradient accumulation, likewise, because we've very little data. Set a small, it's a small model, Whisper, so you actually set a relatively high learning rate, 5e minus 4. I tried a little higher and got more noise, so I think this is about right for turbo. We've just trained for 1 epoch. If you're in Colab, you'll use FP16. We're using BrainFloat 16 because it's supported by more recent GPUs. The max generation length, 128, so Whisper doesn't generate a ton of text. What else? We're not going to save the model at any intermediate steps. We'll just save it at the end and we'll evaluate every 2 steps. I've got dual eval turned on. So with that defined, we're ready to pass our data sets into the trainer with the model and training arguments, pass the data collector and the compute metrics, which does the word error rate, and pass in the tokenizer, which comes from the feature extractor. So with that, we can run training, and let's see if I get something similar. And so we have the 6 training steps, and you can see the word error rate it's kind of falling. The validation loss is definitely falling, and the training loss is maybe a little bit unstable, but we'll see in the outputs if it has a positive effect. Now, when we finish the training, we have LoRA adapters that are now trained. Base model, of course, is not being changed. So you can decide to push just those adapters by uncommenting out this code here. Or what you can do, and I recommend, is merging the model and then saving it locally and pushing it up to Hugging Face Hub. Now, I mentioned earlier, well, actually first, let's run some quick evaluation. So let's run on the validation MP3 and see what kind of data we get out using this trained model. So we can see the results in evaluation.vtt. And yeah, you can see it's definitely better. So phi2 now, it doesn't have the Y. You can see the formatting here. Things like OpenChat is correct. Arena ELO, previously it wasn't even picking that up. It's getting the formatting correct here for Wizard LM 70BV 1.0. So you can see the fine tuning has worked quite well, and we have pretty good formatting compared to what we had previously on those difficult words. Now, if you want to use this custom model, either in your Colab notebook, or if you want to use it as an inference endpoint, we need to save it in a different format. So there are a few formats to look at here. The first is the OpenAI format, the original format. To convert to that, you need to install OpenAI's Whisper, load the model in Transformers, save the model, and you need to set safe serialization to false. This means it will be saved as a .bin, so a binary file, instead of being saved as safe tensors. And with that binary file, you can then run this piece of custom code here in order to get the model converted into OpenAI format. And I've just added in here credit to ndunks for the snippet that allows you to do this conversion. Now, you can then upload that model to Hugging Face Hub as Whisper, Turbo, LLM Lingo. So this just allows you to upload in OpenAI format so you can later grab it and use it within the Colab notebook. Now, the last format is CTranslate2 for faster Whisper. And again, you need to load the model here. So we've got the processor and the model. And next, we're going to convert the Hugging Face format into CTranslate2 for faster Whisper, which we'll use for a server. So install CTranslate2, set up the repo that we're going to pull the model from. We can go from Hugging Face to CTranslate2. We don't need to go via OpenAI. Something that's important is to load the processor and make sure to save that, because we need the processor, where CTranslate2 needs the processor in conjunction with its weights. So we've saved the processor and it's being saved into this CTranslate2 folder here. And then we can run this conversion script that will convert from Hugging Face into CTranslate2. It's quite simple, and it will generate the output file that we need, which is model.bin, the binary file in CTranslate2 format. And then we can upload this entire folder to Hugging Face. So I think that's what I've done. And if you look here on Hugging Face, you can find Trellis CTranslate2. And you'll see here I've uploaded the CTranslate2 format of the model, which has got the vocabulary, the model, the config. And you can check out what that looks like. So Whisper Turbo in the Trellis organization, there's a CTranslate2 model that's trained for LLM Lingo, and it contains the processor and the files that are needed for CTranslate2. And if you really want to, you can even do a quick test of that model in converted format just by running this script here. So at this point, we fine-tuned Whisper for LLM Lingo. We've got it in the Hugging Face format, push to hub. We've got it in the OpenAI format, which can be used for running this audio transcription tool here. And now I'm going to show you how to use the CTranslate2 format with a faster Whisper server, so you can set up a one-click endpoint. And for the last part of the video, I'll show you how to inference or set up a server for Whisper Turbo directly, and then also for a custom model if you want. It's pretty much the same setup process, and it's pretty easy. You can head to the Trellis one-click LLMs repo and check out Whisper here, including Turbo. You can run any Whisper model, by the way, but we're going to run Turbo. I'm going to select an A40, that's plenty. And you'll see here, it's got the faster Whisper template. Now, just quickly to look at this, it's based on a template by Fedirs. So credit there for building this faster Whisper server and the Docker image. And we're going to run the tag for latest CUDA because we want to use our GPU. Now, there are a few environment variables here. We're going to set the compute type to be float 16 because we're on an Ampere GPU. We're going to set the device to CUDA, and we're going to preload some models. This isn't essential, but it means that it will automatically download this CT2, so it's a C Translate 2 version of Whisper Turbo. That's available from the Deep DML organization. Now, if you have a custom model that you want to download, you could just add that in here. So, for example, I can grab the model that I just showed and I'll just paste it in here. And that's going to download both of the models. And we'll be able to choose which one we're inferencing when we make a call to the API. So let's get that started. And in the meantime, we can take a quick look at the README file. So to do that, we'll click on this little icon here. And as I mentioned, you can run any Whisper model here, and you'll then be able to call it using a curl request, or you can use some Python code if you prefer, and the OpenAI client for Whisper. So really easy, just mirrors the same format as OpenAI. You can see there are a few flags that we're going to pass in. So we're going to pass in here in the curl request the name of the audio file. We'll then pass in the model we want to use. So if we want to use the base Turbo model, we'll pass in this model name, optionally pass in the language, optionally pass in the format that we want to get back. So I'm going to take this piece of script here, and the only thing I need to change is my pod ID. So let's head over to a terminal, and I'm just going to paste that in with my pod ID. So I'm going to grab my pod ID here, and I'm just replacing that off screen into the curl request, which I'll then show you when I call. We can check here the logs. So it looks like the image is ready and everything is running up on port 8000. I should have mentioned that, by the way, in the container, we did expose port 8000. And we're now going to be able to hit that via a curl request. And there's one more error here, which is that I need to get rid of the data folder because I just have a validation file without data. So I need to actually read that from my downloads folder. And I'm expecting to get back in V2T format the response to the evaluation text for LLM lingo. Okay, and here's the answer. And this is the base model, so you'll notice that there are still some errors here, like Trixie is spelled incorrectly, because this is not, like this is DeciLM, it's not correctly spelled. And now I'm going to run the fine-tuned version. So you can see that I've swapped the model here, and that's about it. I'm just going to run that now. And there are actually one or two tweaks. Let's just look at the results first. You can see here, we're getting a little bit better performance in pulling out some of the specific names. OpenChat Phi2 is all correct. So you can see this improved performance from using the fine-tuned model. There's one other tweak I had to make, so I'll go back and show you now within my notebook. So when I converted the model, it's very important to upload tokenizer.json. That's not a file that's actually in the Hugging Face repo or needed when you're loading it with Hugging Face, but it is a file that's in the original OpenAI repo. It's right here, tokenizer.json. And it's important that when you convert to C Translate, so here's my C Translate 2 version, it's important that the tokenizer.json be there. So you can just download and upload it manually, or you can download and upload it to the file where you save your Hugging Face fine-tuned model before you do the conversion. And then when you run the conversion, I've now got these flags here that will automatically copy tokenizer.json and also a preprocessor config. So just that final tip, if you want to make sure to get the inference correct when you move to using a C Translate model with faster Whisper. And that's it for the Whisper Whirlwind. I'll put a link to the Colab notebook for doing the audio transcription, either for YouTube, either for base or fine-tuned models. I'll put the link to that below. I'll also put a link to trellis.com/advanced transcription, where you can get the full set of advanced scripts In the meantime, let me know of any questions below in the comments. Cheers, folks.